So the talk today will be about zero cycles, and so that corresponds to section 8 of the notes which are on my website for the Arizona Winter School. Okay? And these notes, I kept on improving them as much as I can, so you can go from time to time and you see so this is the Arizona. So on my web page, you find these notes. Arizona AWS. Lecture notes.
Okay.
Section 8. So it is, okay, so you'd see. Right, so we are, in all the lectures we've had until now, we were discussing the situation of X, a variety of a number field, and then we're interested in X of K. So now today I want to discuss another problem which is connected to this one, which is the question of zero cycles. So I suppose everybody knows what a zero cycle is, but still I would repeat. So we have a variety X over field F variety, and we have a base field F. And a zero cycle, this is a linear combination of closed points. Ni is in Z, and Pi is a closed point. So closed point means, well, it means closed point in the sense of algebraic geometry, but this is equivalent to the fact that, so P closed point, P in X closed point, so is equivalent to the fact that the residual field kappa of P, which I call K of P, sorry, F of P, over F is finite. So given any schematic point of a variety, you have the local ring, the residual field, F of P, so this is a closed point. Okay.
Just an orbit.
Well, so if you don't like, yeah, many people don't like this language of closed point. Closed point really refers to, if you take S equals spec A, it corresponds to maximal ideal. I mean, this is actually a theorem. Okay. So yeah, if you don't like this language, you can think if your field is perfect, you can think of finitely many conjugates which you put together. But I find it more convenient to talk about closed points. You're not choosing and embedding in a specific algebraic closure. So given a closed point, we're given a zero cycle. You have a degree map. So the group is called Z0 of X. So it's the free abelian group on closed points. And there's a degree map, obvious degree map, degree from, actually, I won't do it, I want to do it in a more functorial way. Given a morphism X to Y over F, there's a map F flow star going from Z0 of X to Z0 of Y, which is induced by sending, if you take a closed point P in Y, you take its image, it's also a closed point, but you don't send it to just F of P, but you send it to the degree of F of P over F of P times F of P. So the image is a closed point, but the degree of the residual field might be smaller, you multiply by this. So this operation actually keeps the degree. I'm sorry, these are sort of very well-known things, but I don't worry. So if we apply this to X, to the structural sheaf, spec F, what we get is a map from Z0 of X to Z0 of a point, but that's just Z. And this is the degree map over F, sending sum of Ni Pi to sum of Ni degree F of Pi over F. The degree map. So what else? Now the next step is okay. there's a notion of child group of 0 cycles. So the next step is child group of 0 cycles. So child group of 0 cycles is by definition the quotient of z0 of x by rational equivalence.
Do you assume now that x is smooth?
I'm assuming nothing for the time being.
But that's in rational equivalence.
Well, I'm going to define it.
Ah, okay.
Okay, by definition. So it's this subgroup spanned by the proper morphisms. So I have proper morphism pi from C to x over f, and I have a rational function g in the function. So C is integral normal curve, and g is an element, a rational function, and the function field of this curve, and I take pi lower star of the divisor on C of g.
Okay.
Okay.
Integral
normal.
Ah, normal. Okay.
Actually, I could dispense with the normal, but I can also take it like this.
Yeah, sure.
Yeah.
Okay.
So these are the basic 0 cycles which are decreed to be rational equivalent to 0, and then you take the sum of all possible C's, all possible F's, G. Okay? So that up till now we're not assuming anything on X. It's convenient to allow as much as you can in general.
Sure.
Okay. Now, so the quotient. So this is CH0 of X. Now, if X over F is proper, then the degree map. Then we have a degree map at the level of CH0 of X.
Once again, sorry. Pi star
of the divisor of G on, so we have a rational function here.
Sure.
So we can really take the divisor in a very simple way because it's normal. So at any point of codimension 1, you have a discrete variation ring, take the valuation, and you take the sum of the poles and the zeros.
Didn't recognize characters.
Sorry. The letter, I should write better, that's my problem. Okay, so if X, now next fact is that if X over X is proper, then the degree map, which I prove went from Z0 of X to Z, actually induces a map here. Okay, and that's because if X is proper, then we look at if we have a proper map from C to F, like this. If X is proper, then C will be proper also. I assume that the map was proper here. So C will be over F will be a proper normal curve. And then, then on such a curve, the sum of the degrees, the sum of the sum from all P of odd P of F, multiply precisely by the degree of F of P over F is equal to 0. Number of poles is equal to number of zeros, properly counted. Okay, so we have this map and this degree map. Now, if X over F is proper, we also have a map C0 of X cross bar group of X goes to bar group of F. Defined in the following way. If I take some any pi, close point, and I take alpha in the bar group, I send this to sum for all ni of a co-restriction from f of pi over f of alpha evaluated at the point pi. So alpha of pi is an element in the bar group of fi, of f of pi. And we have a norm map which has to be defined. You have to look at the literature for this, for the co-restriction. You define this map. And it must out by rational equivalence. That's a non-trivial fact. I mean, I will accept this. Okay? So fact. If you believe in beautiful formulas, you can think of it like this: is that you have C, and then you have your function. So the basic situation, like this, where the function G is a map from G to P1. So you start with this pi here, and then you have alpha, which is in the bar of X. And so basically something which is, so what you're taking pi lower star of g upper star of 0 minus 1. Minus infinity, sorry. So I take 0 minus infinity, I pull back, and I apply pi lower star. That's the basic zero cycle of degree 0. And we're pairing this with alpha. So you say, well, this is the same as pulling up here. So the same as g star upper star of 0 minus infinity, comma pi upper star of alpha. Okay. And then this one is, by usual formulas, is the same as 0 minus infinity, formulas which you want to hold, g lower star of pi upper star of alpha. Okay. But now this thing here lives in the bar group of P1F. And this is bar of F. But that's easy to check. And so this is 0. But of course I've been accepting the idea that you have these nice projection formulas all the way through with the bar group. Okay. So now let's go to the case of a number field. So now we take x over k, and then now I'm going to take a smooth projective geometrically connected variety over a number field. And I'm interested in CH0 of x. Now, if you already, when you write this, there is an obvious problem is, what can you say about this group? So I'm going to, what can you say about this group?
Okay.
So there's a big problem, which I'm not going to address at all in the lecture. Big problem is CH0 of x finitely iterated. Is a group of finite type. Okay, so there's more generally, if you take any smooth variety of a number field, it's a big open problem to decide whether the Char groups in any degree are finitely iterated. So in fact, we're not going to discuss this. So, but it's just to tell you that we're going to talk about a group about which we don't know the basic things. But nevertheless, we'll say something, we'll discuss something about this group. Okay, so there's a complex which goes like this. CH0 of x goes to product for all the places v in omega, the places of the number field, of group CH0 of xv. So xv, no, xv is shorthand for, by definition, means x cross k, f, k, kv, completion. And then I'm here to put, I'm going to put a dash here, which I explain in a minute. And then I go to hom, rho of x, q mod z. So there's a complex like this. Okay, I explained that. Maybe I can erase this part, yeah? This part, yeah. Dash, I'm going to define dash.
Is dash related to the product or to...
No, to each of them. So it's just, in fact, it's just dash is just something. So, I mean, to explain dash, I'll first do something. Okay. I'll say what is the map here. So we have a map from CH0 of xv cross a priori bar group of xv to bar group of kv, which is a subgroup of q mod z, which is q mod z if v is finite, which is z mod 2 if v is real, which is 0 if v is complex. Now, if v is Archimedean, this pairing mods out. So if V is Archimedean, so we have KV here, and so I take KV bar, algebraic closure. So I mean, if KV is C, this is just, I mean, KV is C, it's C, otherwise it's R and C. Okay? And this pairing here mods out by the norm from KV bar over KV of CH0 of XV cross KV, KV bar. Over the algebraic closure, you get 0 anyway, okay, over KV bar. And over the reals, if you take elements which are norms of something that comes from the complex, you also get 0. So that pairing mods out by like this. Okay. So if I do a pairing, if I do a map like this, I will never see this part which is more or less the connected component of the business. Okay. So that's why I'm going to mod out. So this definition of CH0, so CH0 of XV dash is CH0 of XV if V is finite, and it is CH0 of XV divided by norm KV bar over KV of CH0 of XV bar of XV cross K KV KV bar if V is Archimedean. Okay. I'll show you an example where you see that when Ray has to do this, to mod out by this. Archimedean. V is Archimedean. A real of complex, R or C.
So if V is a complex point?
0.
Okay.
And if V is real, then you mod out this part.
Okay.
So if you remember what I said about the dual exact sequence for abelian Castle-State dual exact sequence for abelian variety, it was the same. We were on the place we had abelian variety, where the product of the of KV for V finite, and for V real of complex, we got rid of the connected component.
Mm-hmm. Okay. Archimedean place is important here, or could just drop them from?
No. For what I'm going to say, we have to take them into account. You'll see. I mean, I'm going to take the discussion at the end. I'll make the conjecture. I'll write down the conjecture. I'll tell you what this conjecture says in the case when X is the spectrum of a point, and you'll see that there is a good point. There was some good reason to mod out. Okay. So now you look at this sequence upstairs, and then it's a complex. Why is it complex? Simply, so it's a complex because it's just like what we had for X of K, because if we start Z in Z0 of X, and we push Z to this family, the same family ZV, and then we take the sum, and we take an alpha in the bar of X. We evaluate alpha on ZV for all V. This is the map. But if Z comes from CH0 of X, then in fact this is the same as the sum for all V of alpha of Z, which is an element in bar group of F, evaluated at V. But the sum of the local invariance of a global element is 0. Okay? So it's clear that this is a complex. So now a notation, A hat for A abelian group. A hat is by definition the projective limit of the A mod n for all n. Okay? Profile completion where you divide by n. You get rid of the divisible part in particular. If there's a divisible part in your group, you don't see it. Okay? And now the conjecture, which is a really quite strong conjecture, is that for any X over K smooth projective geometrically connected, the complex, so I can take I can apply this functor to this complex, so I get CH0 X hat goes to product for all its projective limits. So it commutes, the product is like projective limits, so they commute, so I can put the projective limit where I want. So here I'm going to take CH0 of XV dash hat, and here I take HOM bar of X, the global bar group with coefficient Q mod Z. And the conjecture is that this is exact. This is conjecture E.
And this dash is not in parentheses?
The dash is, sorry, thank you. Maybe I should put a point here. It might be better. Okay, dash here, and then we have a hat here. But you must realize that at the finite places there is no dash, and infinite places what you have something of order killed by 2. It's either 0 or it's killed by 2. So this product does nothing. This limit just keeps the group. Okay. 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 So example. So I'm not going to start with the empty set. Start with spec F, spec K. Okay. So in spec K, what does it look like? It looks like, well, C0 of spec K is just Z. So what you get here, you get Z hat, product for V in omega finite of Z hat, product for V real, say real, of Z mod 2, goes to Hom bar of K, Q mod Z. Okay, but that's dual to, well, we have a sequence like this, namely we go bar of K goes to direct sum bar of KV, V finite, direct sum, well, all bar of KV, sorry, goes to Q mod Z. So this is the sequence from class 3 theory. And if you dualize it, you get Z hat here, and then you get this here, because for the V finite you had a Q mod Z which gives you Z hat. For V real you had a Z mod 2 which gives you Z mod 2. Okay, so conjecture is true if X is a point. Okay. So, I mean, what is striking about this conjecture is that it's a conjecture for any smooth projective geometrically connected variety. Okay? If you compare with the other conjecture I made in the lecture, for rational points, it was limited to rationally connected varieties. This one for 0 cycles, we are ambitious. We think it might be true for any smooth projective variety.
Okay. I'm sorry.
Yeah?
The first sequence is exact in the middle term?
Yeah, well, there's no 0 here, so it's just exact here. So it means, yeah, if something goes to 0 here, then it comes from the left. So there are two, okay, so this is and then let me right away, I tell you about this, yeah, go ahead.
Yeah.
Sorry?
So if X, say, is a smooth curve.
This will come. We'll get to this. We'll get to this. But before I go to this, I just mentioned that this conjecture E has two sub-conjectures, E0 and E1. So E0 has to do with A0 of X. So we define A0 of X to be, by definition, the part of the Char group which is of degree 0. So over any field, A0 of XF is the part which the degree map is 0. And then you can actually write the conjecture is that A0 of X hat goes to product for all V. And then here I don't put I get rid of the little dash, doesn't count here. I take A0 of X KV, XV, hat, goes to Hom bar of X Q mod Z. So conjecture is that there should be an exact sequence for all places, yeah? Okay. And conjecture E1, which is the one which is more palatable at the first step, is that if there exists a family ZV, V in omega, of 0 cycles of degree 1, such that for all element alpha in the bar of X, the sum for all V in omega of the alpha evaluated of ZV is 0, then there exists a 0 cycle of degree 1 on X. Okay, so we assume that there exists
Of degree 1.
so each ZV is of degree 1, and we assume that we have a family ZV of 0 cycle of degree 1, which is orthogonal to the Brar group. Then there should exist a 0 cycle of degree 1. So for instance, For instance, and in particular, so in particular, if x of ak bro is not empty, then there should exist a zero cycle of degree 1. Okay, so because I just take the rational, so if this assumption is fulfilled, we have simply take rational points out of degree 1, a family of of rational points of the local field, also called the Barrow group. They should exist zero cycle of degree 1. Now, if you think of the lectures we had before, we had all these counterexamples where this thing was not empty, but there was no rational point. But the hope is that, okay, there's no rational point because that's too hard, but you should be able to find a zero cycle of degree 1. So zero cycle of degree 1 is something very tangible. It means that you can find solutions for your system of equations in field extension of co-prime degree. So 2 and 3, for instance, you're happy. Okay. Okay. So
I think also in a in a following fashion, what does mean there exists a cycle of degree 1? This condition is a kind of stable condition. Means the group of cycles.
Yeah.
You could extend fields. Like that.
It's
fields of,
it will be true over any field, yeah, but
it's much more flexible.
Well, and the thing is that it's more group theoretic. You see, I mean, the rational points is some set.
Exactly.
Here is groups. So I mean, this is very okay. So I'll tell more about the history of this conjecture and then the examples where we know how to do it. That's the purpose of the lecture. But let's say, for instance, in the Skor-Bogatov example, we do not know. So this is quite striking. It's been around for now 15 years. So I just look at, there are examples where we know and examples where we do not know. And so I write down the equations because this is a real challenge.
Example, we do not know what.
Well, we know that, so okay, the Skor-Bogatov example, I write it down again. Because I hope that someday somebody will solve it. So you look at a system of equation, y square equals g of t times x squared plus 1, and z square equals g of t times x squared plus 2. And this is an open model, okay? This is an open set U inside X, smooth projective. And sorry? And g of t is?
No, x squared plus 2.
X squared plus 2, yeah. Yeah. And g of t is 3 times t4 minus 54t squared minus 117t minus 243. Okay, so well, we have a completely concrete equation, which is a surface. So we know that in this case, x of aq bro is not empty. This is known. Okay. It's also known that x of q is empty. And the question is, it's clear that you have points in the extension of degree 2 or a power of 2. So the question is, find a solution in an extension of q of odd degree.
Why not degree?
Because it's obvious that there are zero cycle of degree 2 on this one. I mean, if I fix t, then I get this. I can take a value of x, and then I get something. Well, at degree 4 already. So powers of 2 are clear. The question is, can we find something of degree prime to 2? So if this conjecture is true, there should exist such a field. The problem is that you cannot put that on a computer, because at least if you know in which field you're looking for. But if you look at all the fields in all directions, that's too much information. I mean, you cannot. It's too big for a computer. You know, even try degree 3. Degree 3, you have 3 coefficients. To let them grow and try to find whether they have a solution, it's just impossible. So there must be a theoretical solution. Okay, so that's just a challenge. But this has been around since 1999. In fact, the question is raised in the paper by Kolliot-Thélène. Okay, so about the history of this conjecture. So briefly, so if we want to put names in this conjecture, I'm sorry, there will be, there will be, in fact, before that, I would say a castle state. And then there's a paper of myself and Sansuk in 1981. And then there's a paper of Kato and Saito in 1983, 85, well, it was published in 85, I think. And then there's further papers by Saito and by myself, okay, where these conjectures are discussed. So, castle state is basically the case. They didn't phrase it like this, but it's basically, sorry? This conjecture, the conjecture that this conjecture E, which covers E0 and E1. And in fact, it's just, when you write down conjectures, people improve them. So Birch and Snyder made that conjecture, and people improved a bit the coefficients. So in fact, we made initially, these conjectures were made here. This one was not made. So this was improved. So this was stated for the first time in the paper of Van Amel, like this. Van Amel. And then you can read many details in paper by Wittenberg. So explained the history. Let's say the history is explained in Wittenberg Duke Mathematical Journal some 2 years ago. Okay. So what happened is that there was the castle state thing, which people had known for a long time, which was the case of elliptic curves. I say elliptic curves. It's simply elliptic curves. Well, you see there's a sequence very close to this. There were also these things with Poitou-Tate. I should say Poitou-Tate was also some inspiration. In the case of tori. Except that in the case of tori, you can control the rational points. You don't control the zero cycle. So it's just some inspiration. And then what we did with Sansuk was we studied rational surfaces. So surfaces which over algebraic closure become birational to P2. Okay? And Kato and Saito, so we actually produced some results. We had some numerical evidence. So we made a conjecture, which in that case is very simple, because in the case of rational surfaces, this is actually the finite group. This is finite. One can compute in some cases for this group. So we got some, and then Kato and Saito, they say, oh, let's have all varieties without any evidence whatsoever. But it is stated in general. In fact, in a more complicated form. So then over the time, it boiled down to that one, which is really which is clean cut. Okay. So let me discuss the case of curves first.
DMG, Documento Mathematical.
Duke Mathematical Journal.
Duke.
So, and so to add to the history, so then there have been real progress in. So there's a paper of Zalbager. I'm going to discuss this in the lectures today. And then there's a paper of Harpaz and Wittenberg, very recent. So this is progress. Uh, 2014. Okay, so the case of curves. And I am going to make it simple. I assume that x of k is not empty. I can give you references for the general case. Assume x of k is not empty. Okay. Then we're just discussing the sequence A0 hat, A0 of x hat, those product v and omega of the A0 of x kv hat goes to hom bar of x q mod z. And in fact, bar of x divided by bar of k, because the constant part never plays any role here. Okay. So now, what is A0 of x? So if we take a curve, A0 of x with a rational point, that's why I simplify assumption. This is exactly the same as the group of rational points of the Jacobian. So we have Jx, which is pick x over k 0, and which is autodual. So J, there's an isomorphism between J and J hat. So I'm not going to go into this subtlety because we know it's autodual. So A0 of x is just Jx of k. I call it J of k. Okay? I say J is this one. Okay. And similarly over any field, this is true. If you don't have a rational point, there's a subtlety when you compare J of k with A0 of x. But here I'm assume x of k is not empty, so there's no discussion. Okay.
Sure.
Okay. And so now this sequence here looks like what? Projective limit of J of k mod n goes to product for all v in omega of the projective limit of the J of kv mod n goes to hom, and then what? Well, if I have a curve with a rational point, bar of x divided by bar of k, so I claim that bar of x divided by bar of k is isomorphic, we've discussed that several times, with h1k with values in peak x bar. Okay? Because bar of x bar is 0 for a curve. This is Sten's theorem. Okay? So the thing which we have in general is the map from the kernel of bar of x to bar of x bar, but in that case bar of x bar is 0, so we get actually an isomorphism for this curve. And now this peak x bar, there's an exact sequence 0, goes to J of k bar, goes to peak x bar, goes to z by the degree map. But I assume there was a rational point. So there's a split, and the h1 with values in z is 0, so I get that in fact h1k peak x bar is isomorphic to h1kj. Okay. So now I'm going to replace this thing by hom h1kj q mod z. Okay.
Okay.
Yeah?
Silly question. So, say if you take, if you take a model of our curve, it could be, let's say, non-smooth at certain points.
A model over the ring of integers, you mean?
Yeah.
Over the ring of integers, you make explain, yeah.
It will be non-smooth over, and does it affect on? I mean.
No, it doesn't affect the. No, it's. No, I don't see. No, I mean the thing is the computation of J of kv will be more complicated. Mm-hmm. If you have good reduction, you have a disabelian variety, and then A of kv, so it's A of ov, and then you just have the. But even A of ov is a bit complicated because you reduce modular finite field, and you have to see exactly what is A of over the finite field. Mm-hmm. Well, if you have bad reduction, then you have the series of neurominal model where you have these various components. But this is just to discuss the axial structure of this group. But okay. So what I want to say here is that this sequence can be rewritten a bit more. Namely, this I keep, so I keep this J of k hat. And then here, for the finite places, because we know the structure of J of kv, we know that this projective limit is J of kv. So this is product for all v finite of J of kv cross product for v infinite of the J of kv modulo the connected component. And then we have this group here. Okay. So J of kv, it's basically, I mean, J of kv is what? For v finite, it contains, it's a Lie group, it's a p-adic Lie group. So it contains a big open set which looks like OV to some power n, and then the quotient which is finite. And so when we take projective limits mod n, this thing remains itself. Similar for the finite group. So that's why you can replace this projective limit by this thing which is more concrete. Okay. And now what we get here is the famous Castle-State dual exact sequence. It's called dual exact sequence for some reason. And this is, which is exact if SHA of J is finite. That's the theorem. The theorem of Castles and Tate.
Okay.
You see, you can forget about the broad group and speak purely in terms of cup products. Yeah, okay, so let me. No, I'm afraid I have to erase the conjecture at some point. Or maybe I can erase the story. So Castles Tate. So Castles Tate. Yeah, in the box, yeah. So Castles Tate is the following. So if you take an abelian variety A over a field K, abelian variety, so let me say Castles Tate. You take A over K an abelian variety. Locally, you have pairings A of KV cross H1 KV A hat, the dual abelian variety, with values in the blob of KV. Okay, and it's a famous theorem of Tate that if V is finite, this is a perfect duality. So here you have a compact group, and here you have a discrete group. And there's a perfect duality between the group of local, this group which looks like OV to the n up to some finite group.
Which is discrete group?
Which is? This group is locally compact. It's compact, in fact, it's compact.
Yeah.
And this one is discrete.
Okay.
So basically it's something like ZP here and something like QP mod ZP on the right hand side, except that it's more complicated.
Duality between points and, in the case of a curve, and homogeneous.
Species, yeah, you can say it like this, but it's the pair H0 cross. So in fact it's a bit more complicated because A hat, you have to write it as an extension of A by GM. To define this pairing. You have to define this pairing. It's not obvious to define this pairing. It's not a standard cup product. Okay? It's because A hat, in fact, is X1 AGM. So you define a pairing like this. And so now if I take, so again, if I take A of K, I can take A of K ascending to the product for all V. This is the natural thing. Let's forget about the raw groups. You have product of A of KV, and then you can write a complex. Hom H1 K A hat Q mod Z. Here I have a map from A of KV cross the dual of this one. Each H1 K A hat goes to this one, so I have a complex. Okay, at the level of abelian varieties. And then you can take, well, then you see that for the finite places, you get nothing. So you have to modify these things. So let's you put a dash here. Okay. And then the statement of Castles Tate is that if Xi is finite, this sequence is nearly exact. That is, in fact, the closure of A of K inside there is the kernel. So this A of K, it's a group of finite type, but you know it might roll. I mean, it's not discrete inside here. And generally, it's not discrete inside here. So you take the closure. And then one shows also that the closure A of K top is equal to the projective limit of the A of K mod n. And when I say one shows, I should say Serre shows. So this famous paper of Serre in Izvestia, in fact, is used to show that if you look at the topology in A of K, which is induced by the topology from the KV, it's the same as the profinite topology. Okay. Okay. So that's the connection between. So now you recognize what I was saying here. Okay.
I still have.
So what I'm saying is that provided the maps are checked to be the right ones.
No, I just. Particularly, I would like to understand what is. So there is in this box.
Here, yeah.
The product over infinite, over
finite,
points, over
Archimedean places. Archimedean points is G of KV divided by. So it's.
Would you like to say that, say for real points, J of KV could be non-connected? Yeah.
So but the connected part you get rid of it because you don't see it by this pairing.
No, I'm surprised.
Oh, it could. Oh yeah, it can be. Yeah, yeah. It's famous story about. I mean, people have studied that a lot. So there's a long story about comparing. So if you take a curve over the rails, it might have several connected components. Well, yeah, empty curve. Yeah, you have this drawing. Okay, they have two connected components. Yeah.
Okay.
Yeah, sure. Yeah, there's a whole story. And in fact, well, okay, I shouldn't go into the details like this, but this famous duality here of Tate was preceded by the result of Witt in 1934, where he was looking at the reals precisely. And he showed that A of R in his language, that A of R divided by the connected component is dual to each one of R with values in A hat. And in fact, I think Tate in his famous Bourbaki lecture, he says that in the real case, the thing had been thought of by Witt. Yeah. Yeah, I mean, the theory of the reals is a very fascinating story. It's very nice, but this is not the topic here. Okay, so this is to say that at least when there's a rational point, provided you accept that the maps which I've been defined all the way through are compatible, what this conjecture says is simply the Castle-State dual exact sequence. So summary. So I can erase this maybe.
Silly question.
Yeah?
Yeah, about this H1, KV, A.
Yeah.
You told that it is a discrete group.
Yeah, this is a discrete group here.
Why? So
it's well, because it's
approximately why?
I mean, discrete, what does it mean group? There's no natural topology in it. We don't put any topology in it here.
Okay.
But it's a direct limit. I mean, it's a direct limit of the H1 of, so if I take all the finite extensions, KV over KV, of Galois KV over KV, with values in A of KV. Okay, so we're taking at the finite level. Okay, right. So we get this thing which is a finite group, which is a torsion. In any case, it's killed by the order of this group, and it's the direct limit of these objects. Okay. I know one doesn't say direct limits these days. One says something fancier, a co-limit. Okay, so that's that much. So I mean, to summarize, so theorem: if x over k is a curve, so it's always smooth projective geometrically, is a curve. If SHA of the Jacobian of x is finite, then E holds. Okay, and in the notes we'll find references. So in fact, so this was, I mean, several people have written on the details of it. So I sketched the case of A0, but the case of E1 was written. In fact, so Saito has a paper in, I think in maybe 88, in which he claims that he does it, but I never understood his proof, and then so I rewrote another proof. I think 95 or something like that. But it's reduced, you know, it's just reduction. You have to check that everything is compatible. Okay, so.
How often do we know that SHA of, say, an elliptic curve is
finite?
Is finite.
Well, the problem is, in your question, the problem is often. What is the definition of often?
Okay, how rarely?
I think even these people.
Curves to be also for some Colliot-Thélène.
Yeah. So I mean, so the theorems about this are the first person who proved that there exists an elliptic curve with finite SHA was Rubin. Okay, and there were some curves with complex multiplication. And then Colliot-Thélène had a big theorem, which was developed, but I mean, maybe that if you take an elliptic curve over Q, so it's not a theorem of Rn over Q, which is modular, and such that the L function, actually they're all modular now. In the meantime, they're all modular, but at the time they didn't know. Such that the L function vanishes to order at most 1 at s equals 1, then SHA is finite. Okay. No, but if you ask how often, in the sense that if you take P1Q as a parameter space for your elliptic curves, then you cannot count the number of points of height at the height at most h so that the SHA is finite. Okay.
The answers on my
Okay.
Just to say.
Yeah, so there are many cases where people know how to do it, but it's basically sometimes individual class. I mean, there is no. Okay, I can make a statement. I think one doesn't know a single algebraic family of elliptic curves. So you could imagine, you know, can you produce some polynomials A of t and B of t in Q of t, very complicated polynomials, so that each time you plug t in rational, this has finite shell. And I don't know there's no such theorem.
But sometimes we know.
So, sometimes, yeah. Иногда знают. Иногда не дураки. Okay, so that's the case of curves. Maybe I'll keep the conjectures here for a while. Okay, so as I say, well, there was one theorem. Well, I'll say it very briefly because we've talked about these surfaces for a lot. So, so there was a theorem that if you take y square, so these famous Chatelet surfaces, which I like very much, if you take such a surface, so this is my surface U sitting in X over a number field, in that case, the conjecture E holds. Okay. So A is in K star, and P4 of X is a polynomial of fourth degree. So this was proved in 9, well, I mean, it took us 3 years to write the paper anyway, but so in that case it holds. And I just mentioned it because of the way we prove it. Because what we prove is that we prove, so this is a paper with Sansuk and Swendenauer. What we prove is that we prove the result for rational points. We prove x of ak bro. Well, we prove that x of k top is equal to x of ak bro. So we prove this. And in this case, it turns out that if you have proven this, then essentially you also have the other one. And the reason is that there is a special phenomenon here, special phenomenon over any field f. So if I take any field and I take an equation like this, P4 of x, which is a conic bundle over P1 f with 4 geometric degenerate fibers. Over the algebraic closure, I have 4 bad fibers. It turns out that in this case, if I take a rational point, let's say suppose x of f not empty, then the map from x of f to C0 of xf of degree 1 is onto. So any zero cycle of degree 1 is rational equivalent to a point, to an effective cycle. So it's a rather strange phenomenon, which you know for curves of genus 1, for instance, but which is false for curves of genus at least 2. Okay. So you can imagine that in that case, you reduce the problem to problem on rational points. Okay. So it's, I mean, anyway, it's an interesting problem to connect. You know, if you know the zero cycle of degree 1, do you have a rational point? And in general, the answer is no. In fact, okay. But in that case, we had this property, so we could deduce from the theorem here we had for rational points, we could deduce the result for zero cycles. Okay. But the first big progress on the topic was the theorem of Zalberger, which I'm going to explain now. So this is Zalberger. Sorry. No, I'm sorry. I want to say something first. No, this story is not like this. So sorry. No, there will be several steps. Sorry. No, I do. I want to go to Zalberger's result. Yeah, that's right. Yeah. So Zalberger, 1988, I think, or 88, yeah, who proved the following. If x to P1k is a conic bundle, then conjecture actually proved E0 and E1. E0 and E1 hold. Okay, so this was a very special type of conic bundle over there, and he proved that for any conic bundle of a P1. So it's a big encouragement for the conjecture, at least for rational surfaces, because as you know, rational surfaces, oh yeah, I should say the conjecture is birational invariant. It doesn't matter if you have it for one smooth projective model, you have it for another one. It's very easy to show. It's just moving lemma for Chow groups, for 0 cycles. So surfaces which are geometrically rational are birational. This is a result of Iskowski, well, long story, but Iskowski, that they're birational either to a conic bundle over a conic or to a del-Pezzo surface. And del-Pezzo surface is just a finite family. They're very difficult, like cubic surfaces. Conic bundles, you have lots of different types of conic bundles depending on the number of geometric degenerate fibers of a minimal model. Okay? So it's a really a very nice theorem.
This is the theorem over a number field?
Any number field.
Any number field.
And so
theorem of Iskowski over
no, theorem of Iskowski any field. I think he even did it over any perfect field is clear. It's clear in his proof, but I think he actually claimed, and I think he's probably right, that it was over any field, even non-perfect. You have to be careful because smooth is not the same as regular, so you have to be careful. But for smooth, yeah. Okay, so what I want to explain, this is the next step, is on a special case, as I always do, the idea in Zellberger's argument. So I'm going to do a simple case. So
use computation of theory of x.
Sorry?
If you use computation of K theory of x.
We got rid of it.
But did he originally use it?
Yeah, there was some case theory of conic bundles, but we got rid of all the case theory. So the proof I'm giving is, so we over the years we cleaned up. So in fact, this was, so there were further papers by myself and Sundar and Skarbogotov. Because we wanted to generalize the thing as much as possible, and it was too complicated, this conic bundle stuff. So for several, we wanted families of cerebra, for instance, with the generaces. Okay? So this is over the years we've been.
No, I remember your motivation to compute this K theory of family of cerebra.
Yeah. This was this. But ultimately, okay. Yeah, in fact, okay. Let me just concentrate. Okay. So a simple but non-trivial case where you will see how the argument runs. So the basic, idea find a substitute for Shinsen's hypothesis. Remember that in the lectures, I told you that as far as rational process is concerned, if you accept Shinsen's hypothesis, then we know that the Brahman abstraction is the only one for such things. Okay? But now we don't want a conjectural result, we want a result. Okay? So the simple case will be this. So this is the theorem I'm going to explain in details. Theorem. You take K number field. So you look at equations y squared minus az squared equals p of x, and I take p of x irreducible. And do I want degree? No, okay, irreducible, monic. So I'm going to write Cp of x for technical reasons. Monic, unitary, I don't know how you call it. C is in K star, A is in K star. And we look at, this is an open set U, given by this sitting in X, which is smooth and projective. Okay. So I'm going to prove that assume X of AK not empty, then for any integer n at least equal to d, degree of the polynomial, there exists a field capital K of a little k of degree capital N with X of K not empty. So this is so I'm going to prove a special case of conjecture E1. Okay, we're assuming that we have points over locally. Now you might ask, where is the bar group here? There's no bar group. Now the reason there's no bar group is because I took P irreducible. There's no bar group. So it will not appear in the proof because in fact we don't have it because there's no bar group. So if you look, well, here's the bar group. We are assuming that for alpha in bar of x, the sum is 0. But here the bar of x is reduced to bar of k. So there is no this condition. This condition, they don't need it in this case because I choose this very special. See, I choose a very special case where things simplify to the maximum. You still see the idea of the proof. Okay, so I choose this p of x irreducible, which guarantees that this thing is 0. But I'm not going to use that. I'll just say p of x irreducible. Full stop. Okay, and the conclusion will be that for any degree n at least equal to d, there's a rational point. And now you take n and n plus 1, and then you have a zero cycle of degree 1. Okay? So that's the thing we want to prove. Okay, so I'm going to ignore, so I'm going to cheat. I shall cheat on the real places. Let's assume that k is totally imaginary. Say k totally imaginary. You have to do something specific for the reals, which is some manipulation, which I don't want to do. Okay, so it's just we really want to see just the idea. Okay. Okay. So U is the variety defined by this equation. So different from 0. This is U. Okay. Now U. Okay, so what do I do? Okay. Now we define a finite set in omega, as usual, containing all the bad places. That is the places which are where v of a is not 0, p of x is not nice, v of c is non-zero, v is above 2, v is above infinity. Okay, so you can take all these places here. Yeah, that's all we want. Okay, so the polynomial away from S, the polynomial will have integral coefficients. So away from S, P of x, I say P of x is not nice. That means away from S, P of x, which was monic, has integral coefficients away from S. And it has a nice smooth reduction modulo V away from S. So, okay, so that's one thing. Okay. Now, that's it, okay. Now, for V in S, in the bad set, so we're assuming that we have points over locally. So we have U of kV, which maps to, well, P1 of kV. I mean, of course, P1 of kV, but let's say it maps to A1 of kV. And so what I do is that I choose, so I have points over kV, right? So I can find a point over kV which sits inside U by moving, no. I had a point in X of kV. As usual, because of the implicit function theorem, there are lots of kV points. I can find one in U. I can find one in U which doesn't lie above the zeros of P. Okay? So, so I take such a point in a smooth fiber, point NV. And then I move them a little bit. I take n of them. So I have no collinetic section. So I can find different points here. So I find n points like this. And capital N now. Such that in the fiber you still have kV points. That's my choice. And so if this thing here, you define, so define GV of t, a polynomial in kV of t, as the product of t minus these values here, alpha 1v, alpha capital NV. So it's the monic irreducible polynomial that defines these kV points above which we know that there are points in the fiber. Okay? But instead of taking just one, we increase the size. This is the beginning of the Saalberger trick. Instead of just look at one point, you take n points. Okay. So you take this point here, and then you fix a place V0, not in S, such that A is the square in KV0. So we've seen that many times by Chebotarev's theorem. There are infinitely many places in which a Quark expansion splits. Okay, so we can do that. Okay, and then next step, you apply. So P of t was our polynomial here. P of x. Huh? You do Euclidean division for GV of t. So you write GV of t as P of t times QV of t plus some polynomial RV of t. What one I wanted to, oh sorry, for this V0, choose GV0 of t in KV0 of t irreducible. So lemma, a local field, a p-adic local field has field extensions of arbitrary degree.
This bar.
KV0 of t.
This is not a bar. This is.
No, this is KV. So it's this polynomial. I want in V0. I choose a GV0 of t monic and irreducible. On this V0, which is an auxiliary prime in our story. Okay. So for each V in S, we make the Euclidean division where the degree of RV is smaller than the degree of P.
How did you find? I didn't get. How did you find those amount of points beginning with the first one?
Because I repeat. So here this P of x equals 0. This is where we have bad fiber. Okay. Now and then we started with a point which is in a smooth fiber, MV, which mapped to a point alpha 1v. Alpha 1v, alpha 1v. Yeah. Okay. Now the implicit function theorem of a local field tells me that there's an analytic section here. So I can find many points here. Just take the projection. And then so these points which are close to this first one, there's a point in the fiber. So it's implicit function theorem.
Ah, okay. The base is a fine curve.
This is a curve, yeah. It's a fine line.
Okay.
But I mean, the fact that it's a curve doesn't play any role. It would be true. I mean, if you were an arbitrary base, if you have a smooth map like this, analytically, if the map is where the map is smooth, analytically in the number of a point, you do have a section. Sure. So the fact that it's a curve here doesn't play a role. But you want it to be in the smooth fibers.
But you found rational points, as I understood.
No, KV points. KV points. So it is all over KV. It is all over KV.
Okay.
No, rational points. I mean, that would be a dream.
I mean, KV rational points.
KV rational points. Yeah, KV rational points. Yeah.
Okay.
Yeah. Okay. So we make this division here. Okay. Now each Q. So we have to keep track of this thing. This thing is of degree n.
So
yeah.
A question. So GV0 and GV.
Yeah.
So they are really different. So they have no connection.
No. I mean, the GV is for V and S. They have the same degree. Yeah. It's an auxiliary thing which we want to see because in the end, I mean, in fact, this GV0 is purely psychological. If you allowed me étale algebras rather than fields, I could ignore the GV0, I think. But it's if I pick an irreducible GV0, in the end it will produce an étale algebra which is a field. So psychologically, it's simpler. Okay, so we're here. And so now, what do we do? I was talking about the degree. So this one is of degree d, this one is of degree n minus d, and this one is of degree smaller than d. Okay, good. Okay. So now we're going to approximate these various things here. the QVFT and the RVFT. Now, so what do I want? Okay, so let K, this is not this K here, I'm sorry, this is, I should say an L here. Let K be K of T divided by P of T. So this is a field here because I assume that P of T is irreducible. This is specific to this case. Huh? Okay, so it is. Okay, now did I write everything? So RV of T is of degree smaller than D. So if I look at RV of T in KV of T divided by P of T. This is K tensor KKV. So I get this RV of T defines for me an element in this product of local completions, which I call psi V. Okay. So for V in S, RV of T defines this psi V in K tensor KKV. Okay. This is for V in S. Okay. And now you use, so this is the next step, we use Dirichlet's theorem to produce, so let's say, stick to my notations, probably better, to produce a psi, yeah, that's what I want to, a psi in K star, which is very close, psi minus psi V. So this is a psi V. V is smaller than epsilon for V in S. Additively or multiplicatively, it doesn't make any difference here. This psi V is non-trivial. Okay. Yeah. And the decomposition of psi in capital K star is of the shape, so the decomposition in capital K star is 1 prime, so there's one auxiliary prime, 1 prime here, which I call what? 1 prime W, say PW, products of primes V, which are in S. So you're in a number field, you have finitely many completions, so this is for each V in S, there are finitely many completions here. You have elements in these completions, and the claim is that you can find a psi in a number field, which is very close to each of these elements, and the decomposition of which is nearly a prime. So you have some things here with the PVs here with some power NV, which you don't control, which of course you don't control because the psi is very close to the psi V, and psi V could have poles or zeros, but it is near a prime. This is Dirichlet's theorem in the field capital K.
It's not prime only because of bad.
No, because it's not prime because of bad things. Yeah, I mean this is generalization of Dirichlet's theorem about A n plus B when A and B are coprime integers, yeah. But in a number field that's the way it reads. So you know when you take X plus B.
Let's suppose the base field is rationals. Then what do you state?
No, but here it's when in case. We were talking about the field extension anyway. Yes. But yeah, in the case of the rational, directly in the case of rational is simply saying that if I take Q here, okay, and I take finitely many alpha, so I take S, a finite set of places, and I take elements alpha P and QP star, then, and for P in S, then there exists alpha in Q star, so that alpha is the decomposition of alpha, we see of the shape a prime L times product of P to the power NP, and the alpha is very close to alpha P, called P in S. That's what I'm saying. Okay. I mean, this is the analog of the congruence conditions, and this is a prime that remains. When you take ax plus b, you want the congruence modulo the primes which divide a, and then it remains a prime. Okay. So we get this psi here. Okay. So and then for q, so this is what we're doing is that this psi now we lift it to a polynomial r of t in k bracket t. Okay, because
what?
But we leave this psi now, k of t divided by p of t is capital K. So we produced an element psi here. We lift it to a polynomial r of t of degree smaller than p of t. Okay. Okay. We lift it to a polynomial r of t. And of course this, well, okay, and this is for the r of v of t part, and for q to define q of t in capital K of t, monic, integral coefficients away from S union V0 and close to each QV of t coefficient wise for V in S. So what we're doing is we're doing stronger approximations of the coefficients of Q. Of the polynomial Q of t. It's monic, so the first one we do nothing. The highest one we do nothing, it's 1. But for the other ones we approximate by strong approximation. So strong approximation, again, you have finitely many places of elements in KV. You can produce an element in K, which is very close to each of these elements, and such that it is integral away from S union 1 place. And this place you can choose. So we choose this V0 which we had here. Well, it's actually it's.
No, but at least inequality for that.
Well, it's at most d. Huh? It's at most d because when we do this lifting process, we lift to the unique polynomial of degree at most d, which is there. That's the way we define it. So, okay. I mean, there is nothing more because the RVs could have different degrees. Okay. Yeah. Yeah. Okay. Okay, so we have reached this point. Okay, the case n equals d is allowed. In that case, the q of t is just 1. This, if the degree was the same here, just 1 here. Why not? Okay, but let's ignore this. I mean, we have this g of t which is of degree capital N.
Yeah.
N was at least equal to d. It could be equal to d. And then if it's equal to this polynomial, then I'm just taking the difference. I get something of degree smaller. This is the trivial case of Euclidean division. Okay.
We have chosen GV in such a way that the RV is not 0. So yes.
Yes, because this corresponds to points which are away from P of x equals 0.
Yes, but
I mean, if this was 0, then what would it mean? It would mean that if I plug in the 0 of P, that would vanish. It corresponds to, so no, we're in the smooth fibers. Okay. So the RV of T are non-zero. So I did say, this is why I put this star here.
Or roots maybe in extensions also.
Yeah, but what we want to avoid anyway, we want to be in the smooth fibers. So in the smooth fibers, this will be non-zero. Yeah, the roots are wherever they are.
Exactly in the field K of V, KV.
Yes.
Yeah, they're very close.
The section is isomorphic to.
But this is just in small neighborhood, okay?
Yes.
Neighborhood for the V-adic topology. Okay, so now define G of T, global field, with the global field as, so we have a P of T times a Q of T plus R of T. And now this is in K bracket T of degree n.
So before we had family of polynomials, now we'll get just one.
Yeah, we
I mean,
we have a family of GVs,
yeah.
and now we have found a global one. Okay.
Which is very close to those ones.
Well, exactly. So, so first of all, for V in S, and union V0, G of T is very close to GV of T. So I'm talking nonsense with V0. I think I'm talking nonsense about V0. Sorry, for V in S. But no, I want V0. I wanted this V0. No, wait a minute. I know, I did something stupid. I kept this V0. I should have kept it. No. I mean, we'll always keep on introducing new primes. I needed 2 primes. So sorry. Sorry. I'm sorry. Sorry. So we have a V0 not in S with this property, and we have a V1 not in S with this property. And KV1 is not in KV1 square. And different from the other one. And then, so here, when I do my strong approximation, I do it away from VS union V1. So I do not know whether I'm close to V1, but I'm close to V0. So that's correct. No, this is correct. So for V in S union V0, G of T is close to GV of T. Okay, and it is integral. So G of T is integral away from S union V0 union V1. Well, so I tell you, so the V0 I wanted, because then, and G of T is irreducible because G of T is very close to G of T at V0. So G of T close to GV0 of T at V0 implies that G of T is irreducible. Okay, so I wanted an irreducible polynomial. That's why I use this prime V0.
My point is, and my question is, why do you interested in irreducibility of G of T? Because
the polynomial, because the field L I'm looking at is L is, we take L to be K of T divided by G of T.
So because you want to construct not an algebra, but...
Yeah, exactly. Yeah, so it's purely...
Okay. But psychological, this is...
It's psychological. It's slightly
more difficult, I would say.
It's just, it's okay. Okay, so now this is a field extension of degree L. Of degree capital N. Okay. And then we let theta, so let theta the class of T here in L. Okay, well, that's all right. Okay. Now theta is integral away from S union V0 union V1. This is why I'm saying that G of T is integral away from S union V0 V1. Okay? Okay. And now take rho to be the polynomial P evaluated at theta. Rho, by definition, is P of theta, which is an element of L. And the claim is that now, if we go over this field, we'll have a solution. So let's say I think I can erase this. Maybe not. So the claim is that if I look at y square minus az square equals c times p of theta, which is a conic over the field L, as points in L, as L points. Okay, so we, therefore, which implies that U of L is not empty. So we find a closed point on the A1 such that the fiber has a rational point.
How does it relate to the original this equation? And what was
Well, the equation is here. I wrote it here.
Sure.
I wrote it
But
here.
the original equation was okay.
Here, it's this one. So we plug in x, this value, I should have called it t. I mean, okay, whatever you call it t if you want that. So we plug in this t, we plug in theta inside here.
Yeah.
And the claim is that if I look at this conic, so this is a closed point, I evaluate at the closed point of the A1.
Over the field A.
Over the field L, yeah.
Okay.
Okay.
Yeah. And this conic splits.
Well, that's the claim. And then that will imply, that's the claim, that will imply that U has a point over L. So we'll have produced a field of degree n over which the variety has an L point.
Okay, yeah.
Okay, I mean, we produce, instead of producing a rational point here, we produce something here of degree L, so that the conic has a point over L. That's the claim. Okay.
Yeah. We didn't prove this claim yet.
No, but this is the last claim, in fact, because if I prove this, then the theorem will be proved. Okay. Okay, so now let's see. So if so let's see. For places V, W of L, which are above places in S. I say that this is clear. So why is it clear?
Would you like to apply local principle now?
No,
To this
conic, yeah, to this conic. But so what we'll show is that this conic has points in all the combinations except possibly one. That's what we will show. So this is the what we did in the initial argument, where we have a rational point. We found a rational point where the conic had points in all the combinations but one. Now we do that over some suitable field where we actually prove that there are points in all the combinations except one. Okay. So for places, so the idea for places which are above places in L, the idea is that we're close to the original situation. So let's see what happens. G of t is very close to GV of t, okay? And so places which are above places in it, G of t is close to GV of t. So that the field L, which is, I remind you, is K of t by G of t, just breaks up at these places by Krasner's lemma. This L tensor K KV would just be a product of KVs. Okay, GV of t was this product of local things. And above these places, we had solutions. So when we go over, so if we're over, so here we are.
I think it's better to do not use the subscript V now.
V?
In this form. KW is fine. But
No, but okay, if W, which is above a place V in S, then G of t is close to GV of t, and so L tensor K KV for V, which is at the bottom, is simply product of KVs.
Okay.
KVs for corresponding to the from running from 1 to n.
KWs. Sorry.
No. If so the field L is over K, but if I take a place W which is above a place L, in fact this is of degree 1. That's my claim.
Why?
Because so when L is K of t divided by G of t. But G of t, so if I look at L tensor K KV, I find KV of t divided by GV of t. G of t, but G of t is very close to GV of t. So it's isomorphic by Krasner's lemma to kv of t divided by gv of t. Okay, and this gv of t is just given by this product of local points, where we had local points upstairs.
Okay, now I got it.
Okay, and so the conclusion is that for places in here, we find that there is an LW point. So the conic C of LW is not empty. I mean, the drawing is that see, we have this L point, okay, and the conic here. But when you go over to kV, it breaks up into these finitely many kV points. And these finite kV points had points locally. So C of LW is not empty. So these are the places which are above places in S. For places above V0 or V1, there's no problem, because A is a square in KV0 and in KV1. So if W in omega L is above V0 or V1, A is a square in L W star. So the conic, so A is a square, therefore this conic obviously has a point. Okay, and now comes the crucial thing, is we want to look at the other places. Okay, so what you do is that you look at the formula, so you have two polynomials G of t and P of t. And so you look at the formula for the resultant of two polynomials. The product of the G of the roots of the other one is equal to plus or minus 1, the product of the P of the roots of the first one. Okay, so it says, well, let me write it down. So P of theta, what is P of theta? P of theta, theta is theta is the class of t. Okay, so C of theta is a root of G of theta. G of theta equals 0. Okay, so the product of the P of theta I, if I take the roots of the other one, is equal to plus or minus 1, the product of the roots of G of, I'm getting lost here.
Write down kind of reciprocity.
Yeah, no, but it's polynomials. It's as ancient as mathematics. I mean, so if you have two polynomials, I mean, of course, the reciprocity law, which you think of in K2 for K2, is a generalization of this. But if I take two polynomials over an algebraically closed field, if I write product of t minus alpha I, and then I have product of t minus beta j, it's clear that the product of the alpha I minus beta j. So, yeah.
But I'm about the meaning. I'm not
the meaning.
No.
Well, the meaning, the philosophy here is okay. So theta I are roots of zeta, roots of G, and here I take the product of the G of the roots of P. And so what are the roots of P? The roots of P have nothing special, so what do I do over the roots of P? Well, let's call it beta, beta j. Okay. So, well, okay, let's get okay.
Okay.
No. Lambda, mu, nu, rho, omicron. So after alpha, beta, gamma, delta, theta, eta, you're right, eta, you're right, good. I see you're going to Greece. You're going to Greece. Okay, so now, I'm nearly finished, but yeah, okay, sorry. Yeah, but in fact in my note I call it alpha. So, yeah, alpha is a class of t in k of t modulo p of t. So alpha, class of t in k of t modulo p of t. Okay, so the alpha j. And then I have this equality defining G upstairs. And so I look at what happens. So G of alpha is equal to P of alpha, Q of alpha, plus R of alpha. Okay. But P of alpha is 0. Okay, so G of alpha is R of alpha. So this is plus or minus the product of the R of alpha J. So what? Yeah, so P of theta is the one which I want to control here. Okay, okay. And now we remember that this psi was chosen so that, remember, this R, the class of R here was of the shape, so R of alpha here in this field was a prime P uncontrolled times product of other primes which are in S. One prime. Okay.
Is it psi?
This is the psi. Yeah, this is the psi. Exactly. This is the psi we're chosen. Okay. It was a shape P because yeah, this is the way psi corresponds to R of t. Okay, it's up there. Psi corresponds to R of t. So yeah, R.
Now we have several many.
No, but the class of t is no. Alpha is a class of t. See, so R of alpha is psi. Look at this. K of t modulo P of t is capital K. Okay. So alpha is a class of t in here. R of alpha is psi.
But we have several many.
There are several alphas. Okay, so several.
And do we have several many psis after that?
Okay, so no. Okay, now the. Let me see, just 1 second. Psi is R of alpha. There's no doubt there. It's here, because psi R of t was defined by the class of psi here. Okay.
Sure, but my question is there are several many.
Yeah. Okay, sorry, we're thinking about this.
Alpha is a generator of a field L, yes? Or
Alpha is a generator of.
L, yes.
Where's alpha?
Oh, no.
No, it's theta is a class of T and L. No. Alpha is correspond to capital K. It's a class of T, so it's a generator of capital K. This one. No.
Maybe there is a confusion in notation.
No. Psi is R of alpha. T is a class. Alpha is a class of T in K of t modulo P of t, which is up there, and so and in R of. So I mean.
But how alpha relates to alpha J?
The various. Okay, so let me think for a second. We want to see that in P of theta, all the primes are controlled except one. That's our aim. Okay. So this P of theta, we have it on the left-hand side. Okay. And okay, so that's a norm really. This thing is a norm down to K. Okay. So what we're taking is we're taking the norm of. So we're taking plus or minus the norm from capital K to K of the R of alpha. Okay. Now, so if I take the norm here, I get bad primes, and then I just get the norm of this prime P. So there's just one prime here. One prime, unknown, and then things in S. Okay. So now this P of theta, which was the thing we were interested in, this P of theta here. Also, again, it was integral away from. We look at it in places where P of theta is integral. So we find that the norm. So the places which are not in S union V0 union V1. So if I take my place W, place of L. W not above S union V0 union V1. Then P of theta is integral, is OW integral. And we take the norm from L to K of P of theta. And we find that in the decomposition of primes, there's just one unknown prime times product things which are in S. Union V0, union V1. Okay. So now P of theta upstairs, the norm involves just one prime. So what could happen to P of theta in the decomposition of P of theta? We could have, okay, now the problem is we might have several primes. Okay, but now we solve this problem because something I didn't tell you is that I will get a prime with exponent 1 here. Okay, I'll get a prime with exponent 1 here. And how do I get a prime with exponent 1 here? Is that in this norm here, it appeared the norm of this prime P.
Yeah.
But when you use Dirichlet, when you take Dirichlet's theorem in a number field, you can not only choose a prime, you prove that, so you have your psi v at finite many places, which are approximated by a psi. So this psi is a product of some prime times things which are in S, and it's close to the psi. But this prime, you can choose it of absolute degree 1 over Q. That's, well, absolute degree 1 over Q. So that the prime which will come up here, which we had here, this psi here, this prime is absolute degree 1.
So it means that the norm of it is just a prime.
It's just Riemann itself, no exponents. Okay, so that here we have a 1 here. And then now we're in business. Because the norm of this thing, which is integral, has just one prime unknown to the exponent 1 times something. But then upstairs, we can only have one prime missing. I mean, if we have two primes, the norm would have a power here. Okay, so that's that's a key point here. That in Dirichlet we use this specific thing of this Dirichlet.
What is the conclusion?
Well, the conclusion is that now P of theta. So thank you. The conclusion is thank you. The conclusion is that P of theta. So conclusion. Is that the decomposition of P of theta in L is 1 prime times product of, so this is in L, primes W which are above S union V0 union V1. Okay?
Okay.
P of theta in L, it's just this one prime, and primes which are, there's just one prime here, which we don't know. Okay? Yeah. And now we're looking at our conic here. And look at CFP of theta. Sorry. You look at CP of theta, and if you're away from this prime, this thing is a unit. Okay, we put in S, so C was a unit away from S. So this thing is a unit. This A is a unit. So this conic has points in the completions. Yeah, the prime, which is y squared minus a squared equals some constant, and both of them are units in your number field, and you're away from 2. This is a solution in the completion. So this conic has solutions in all completions except possibly at this unique prime, and so we're finished.
Okay, by reciprocity.
By reciprocity. So use reciprocity here, and in the next hour, we'll see how the Arpas-Witten method avoids this reciprocity argument. But it's really, it's a complete, I mean, this is really a very elaborate argument, which Zalberger found.
Sure. Let's see, would like to ask you, I mean, not to sketch, but to stress the key points of the very last arguments, beginning with resultant. So you have this equality product of P tilde I equal to product of G of alpha J, and then what was the key point?
The key point is that you prove that the P of theta involves only one. There's only one bad prime in P of theta. The other ones are all controlled.
On the right-hand side, we have the norm.
Yeah, we have norms on both sides. I mean, there's norm from one side, there's norm from the other side.
Norm, right, on the both sides. On the right-hand side, we have norm of at the point
From cut
at the point
this
alpha.
So this is the norm from L over K.
Yeah.
So this is G, a root of G. Okay, so it's norm from L over K of P of theta. And this is plus or minus norm from a capital K over K of G of alpha.
Okay. Yeah.
No, I mean, I can try to do something with more geometry on P1 OS. Try to explain more with geometry and P1 OS what happens.
I almost got everything. Just okay. You have this equality of the norm.
Yeah.
Then you you take a look on the right hand side. Means on the norm of G of alpha.
So the psi had been chosen. So the psi was this thing which was where you control just there was just one bad prime on the psi side. So
but norm of G of alpha is the same as norm of R of alpha.
So psi is, I repeat, is R of psi is R of alpha. Psi is R of alpha.
G of alpha.
I'm sorry. I'm talking nonsense. Psi is. Yeah.
G of alpha is the same as R of alpha.
Yeah. That's the point. Yeah. So, thank you. Okay. And this is psi.
And this is psi. Now you take a look on the norm of psi, and the very key point is that the norm is just 1 prime times
1 prime to the exponent 1.
To the exponent 1
times bad primes which are in S, above S union V0 and union V1.
Okay.
And then it forces the same thing on the other side.
This forces what?
That the norm from L to K now of this P of theta is also just 1 prime times products in S. And this P of theta was integral away from S union V0. P of theta was integral, I repeat, this P of theta was integral away. Because of course you could, if you had nominators and denominators, they could cancel. But P of theta is integral away from the S union V0 union V1. And I know that its norm downstairs is some prime times things in S union V0 union V1. Therefore, in the decomposition of P of theta in L, of P of theta in L, we have primes in S, in above S0, but the other ones are integral, and the norm of that thing is just 1 prime.
So
1 prime, and so therefore there can be just 1 prime there. And that's because of this strong form of Dirichlet. So I use this strong form of Dirichlet.
So the conclude.
So strong form of Dirichlet.
So P of theta is integral, and there is just 1 prime in P of
theta in L.
Which is?
Well, but we know nothing. P of theta. If I look at P of theta and the various valuations, for away from S0 union S1, we don't care because we know that this thing has solutions. And the only prime, there's just 1 prime which we do not know. Apart from that, it's a unit. It's a unit in the other completions. So therefore, in the other completions, when you look at this equation, A is a unit. In the other completion, C P of theta is a unit, and therefore that has solutions in all these other completions.
So the idea that an idea is to prove that P of theta is a unit out of just 1 prime. We don't know this prime.
Yeah, exactly. This is the analog of what we did with Schinsel. We had just 1 prime missing, but
and for other primes, we just
we had this. It was close. The other primes were very close to places where we had solutions, so we knew it, or where we had trivial solutions because A was a square.
So for the other primes we did.
Other primes we use approximation. And for the very good primes, we use the fact that the very good, if it has good reduction, the conic has points, the completion, and there's just 1 prime where we do not know.
Okay. I'll say just before the break. My question. How Zelberger
found this?
No, it did use K not or K theory.
It was to translate CH0 into. Of course, I give you a very simple case because I started with rational points, but it's not important.
But in any case, he needs to use strong approximation. He needs to use.
Oh, sure. All this also was used. Yeah. But in fact, the point is that he had a translation which is quite complicated. Of this is what the case here was in. Is that if you take so forget about what I said. If you have a conic bundle over a curve or arbitrary genus, in fact, you look at the map from the degeneracies, but the map is proper. The curve C is smooth. You can look at the group CH0, the relative group CH0 X over C. So the cycles which die when you push them down to C, and you can show that in fact they're the same as the set of functions in KFC star, which equals CFC star dn modulo reduced norm. So this is where there's some case here that comes in. These are the functions on KFC.
So this K1.
There's this K1. These are the functions in KFC which ever locally on the completions at the close point of C can be written as unit times the reduced norm in the completion. So there's a translation here, and so he was. We're interested in a statement about that group. He first used some case theory, not very complicated, to translate this group into this group of functions.
So this K1, you can write down some kind of guessing for K1 or local.
Well, it's. I mean, we can discuss that later. Okay. Maybe we can discuss. I can show you that. This is purely field theoretic. I mean, this is not over a number field. This is purely, and then, well, it was really quite complicated, this argument. I mean, this is really streamlined, because afterwards you have to define maps. Okay, it's more complicated. So no, the thing is, I mean, you could try to think algebra, to make a drawing to understand what happened.
Okay. Yeah. And then break.
And then break, yeah. But I mean, I repeat, in this special case I showed you, you have seen in this special case I showed you, this is the simplest case I can think where you see all the arguments that go into the proof of Gerald statements later. Okay. So what are you doing? You're doing the following. You started with your x over P1k. And then, so this is P1k here, and this is spec k. And here's the spec OS. S union V0 union V1. Okay. So you have this polynomial P of t, which is here, in our case, which is some close points. So this thing goes to, well, it's and then we are looking for another point which will be defined by g of t. And we want this above g of t. We have the conic bundle. We want the conic bundle to over this close point g of t. We want some solution. So the problem is what happened at the intersection points like this. See, because away from the bad locus, so you can choose the OS in such a way that if you look at a close point here, M, close point, which doesn't lie in P of t, then the fiber above that close point will be a conic with a rational point. So we can arrange. So choose the S such that for all points, close points M in P1 OS, so we have extended the conic bundle X, which we had over P1K, we've extended to some model X over P1 OS. Okay. Such that for any close point in P1 OS which doesn't lie, VM doesn't belong to this closure of P of t, so P of t equals 0, then the fiber xm over the field f of m is not empty. It's smooth and not empty. So when we look at our field L, we're looking at what happens over this thing here. This is our conic over L. We have this family of conics, and we have the conic over G of t equals 0.
Projection is going there, right?
And well, no, it's not a rational point. So okay.
No, the projection is going.
Well, it's G of t. Okay. This corresponds to this, and this corresponds to P of t. Okay. So the projection. I mean, I see the conic bundle above it. No, conic bundle. The conic bundle is over this. Okay. So we have a family of conics. So we have conics over all these things. Okay. And over spec L, we have a conic here. And then this conic, we look at it over the ring of integers, okay? And so we wonder whether in all the completions it has solutions. So at this point, there's no problem. And so all the fight is at the point where these two things meet.
Okay.
And so what we arrange with this magic here is that you arrange that there's just one point. There's just one point, and moreover, this point is of degree 1 above this one. Okay, this is this formula where there's just one bad prime. And so.
So we. Okay.
So let me say one more thing is that ignore this.
So one point. So but this G of t could be a huge degree, right?
No, we show. So for the argument to work, we must be able to do this Euclidean division. This is the key point. So that's why any n which is at least equal to the degree of p is okay. I mean, the philosophy behind this, if there is a philosophy, is that if you take as soon as you take a symmetric product of your variety of degree at least. Because I mean the point of degree n, that corresponds to the rational points on the symmetric product. So somehow is as if you could translate if you go take a symmetric product of a degree which is bigger than the number of geometric degenerate fibers, then you manage to prove a local global principle for rational points on the symmetric product. But it's just an idea. I mean, I cannot justify it with a concrete thing, but this is the thing which is magic here. And there is something to that, namely that there are theorems that if you take a conic bundle over P1, I say that if you have a zero cycle at D1, you don't have a rational point. But there are theorems with Zalberger that say that if you take, there is an integer which only depends on the number of geometric degenerate fibers, so that any zero cycle which is of degree at least equal to that integer is equivalent to an effective cycle. So that's
so there's a point on symmetric product.
So there's a point on the symmetric product. That's basically what you were proving here. It's just, I mean, we haven't understood that completely, but it's basically certainly what we were doing here. Yeah? I mean, something which I find, I mean, from the geometric point of view, I find fascinating, and I have no idea. This is going to be even vaguer. Is okay, local global principle or Brauer group is not enough for rational points, but it seems that in a number of cases, symmetric product is enough. Okay, and I compare this with a statement which I've never read the proof of in complex geometry, which is I have read that people can prove this, that if you take a smooth projective surface over the complex field, and you take at least S2 of x, the symmetric this Hilbert scheme of points of length at least 2, then the pi1 of that thing is always a billion.
Okay.
The pi1 of the original thing was not, but the pi1 of this one becomes a billion. And so I mean the totally crazy idea is that maybe this is the thing why zero cycles. You manage to prove something because your Brauer group and pi1 and Brauer group will be enough to control what happens. Because if you take symmetric products, you kill this problem with the non-abelian pi1. But that's just, it's totally a crazy statement.
I would like to say that, since you make a pairing with Brauer group, and Brauer group is homotopy invariant.
Yeah.
Yeah. Then if you so take infinite symmetric product.
Yeah. Okay. Well,
yeah.
Let's be open-minded for a second.
Yes, infinite symmetric product, and you have a map from U to infinite symmetric product. In fact, this is just core from U the finite correspondences from U to
U is what? U is
U is just any.
Oh, any space. Yeah.
Yeah,
Okay.
For instance, U is.
No, okay, some space.
Speckle field.
Okay. Is what is?
Speckle field.
What's speckle field? Yeah.
And then you take this core from speckle of any field to your infinite symmetric product and mod out, because the pairing factors through the homotopy.
Yeah.
Homotopies. It factors through zero cycles. I mean, point is that the zero cycles are exactly the.
Yeah.
There is monoid.
Yeah.
Monoid, which is the infinite symmetric product. The points on infinite symmetric products. And if you first take the associated abelian group.
Yeah.
This is the group Z0.
No, but the point is you're taking infinite. So I think the problem is here we want to take a finite stop somewhere. We must want to stop somewhere.
And where and how we control the finiteness? Because we have this division Euclidean division algorithm.
Here.
Yeah.
Oh yeah, here. Yeah. So in fact, and okay, well, maybe I should stop. I suppose. No, and I wanted to say one thing is that Zalberger, the original argument, the Schinsel argument, was using, conjecture generalization of twin primes, for instance, or things like that, t plus 2. Okay. And something I noticed is that if you want to understand a bit what Zalberger does, is that basically what you prove is that, well, we don't know twin primes of a Q, of a Q. But here's an easy fact, completely trivial, is that for any d at least equal to 2, which happens to be the sum of the degree of t plus the degree of t plus 2, there exists a field extension, L of a Q, of degree d, such that, and an element alpha L in L, such that alpha L is 1 prime times product in a bad set, but very controlled, say above 2. And alpha L plus 2 is also a prime times product set of a bad set over 2. So you can produce some suitable field for any degree, except one, which is the one you're interested in, you can do twin primes.
You can do?
Twin primes, because this one is nearly a prime, and this alpha plus 2 is a prime. And it's completely stupid, because basically what you do is that you take polynomial P of t, you take some polynomial P of t times t plus 2, and then you choose the prime, plus P of t plus q times t plus 2. You find R of t like this. P of t in Z of t. And what you find is that P of t monic, and if you arrange it to be reducible, well, the last term as a polynomial in t is what? Is 2q. And the last term as a polynomial in t plus 2 is 2p or plus or minus 2p. So your integer alpha, on one side the norm is 2p, on the other side is 2q. So you're done. So it's... and somehow this construction of this polynomial g of t is very much in this spirit.